Okay, everyone, thank you for coming, the people that came in person, also for people that joined online. So today is a pleasure to have here Miranda Holmes-Cerfon. So she's an associate professor at NYU. She got her PhD also in NYU, I believe, in 2010. And after that, you moved to Harvard, the CS as an instructor. And then after that, then you went back to the NYU. So she has actually a very interesting work, very impressive in many different fields that she's touching on. So she develops tools that she applies to statistical physics, also to computational geometry, and applications that are ranging from biology or materials or fluids, also ecology. So I think that was quite interesting. And today you are going to talk about some application to simulating particles and some short-range interactions. So with that, we are very happy to have you here, and please go ahead.
Okay, thank you very much for the invitation. It's really a pleasure to see faces. I think this is sort of one of the first times I've given a talk in person, not to a screen. So thanks for this opportunity. I'd like to start by acknowledging, if I can move my slides, the people who contributed to the work that I'll talk about today. So notably Nawaf Bourabi, who is a collaborator on the second part of my talk when I'll get to dynamics, Jonathan Goodman, a colleague at Courant, and Emilio Zappa, former postdoc, who collaborated on the first part of my talk. And then many others that I'll mention as we go through. So my talk today will be focused on particles with diameters of nanometers to micrometers. And such particles, they're often called colloids, generically. And such particles form the building blocks for many of the materials that we see around us. So I'm showing some examples here: mayonnaise, paint, opal, toothpaste, et cetera, et cetera. And when I say they form the building blocks for these materials, what I mean is that the macroscopic properties of these materials arise from the microscopic interactions between these particles. So for example, the fact that paint stays on the paintbrush, but then it comes off when you push it on a wall. Ketchup stays in the bottle until you squeeze it gently or tap it gently, and then it spurts all over the place. Those kinds of macroscopic properties. We can understand them by thinking about colloids, but we don't need to go to even smaller scales. We don't need to go to atomic scales in order to understand these materials' properties. Such particles are also used widely to describe biological materials, even if the materials are not necessarily made of actual sort of lumpy particles. They're often modeled with particles in simulations of such materials. So for example, networks of fibers, such as actin networks that make up the interior, that give cells their structure, these are sort of networks of fibers that are bound by crosslinkers, and the fibers in a computer will be modeled as strings of particles that are linked together by springs. And then the crosslinkers might also be dimers of particles, also bound by a spring. So these kinds of particles on these scales, they're both small and large. So they're small enough that when you put them in a fluid, they move around randomly because of the thermal fluctuations in the fluid. They're small enough that they actually see those fluctuations. So this is a movie. Whoop, no. How do I start this movie? Is it? Yeah, okay, so you should see a movie. This is a movie looking in a microscope at a suspension of colloidal particles. They're about a micron in diameter, a millionth of a meter. And you see them just jiggling around randomly. This is Brownian motion. And then eventually the particles will sort of find each other, and they like to stick to each other in this experiment. These particles are also large in the sense that they're larger than atoms. And in particular, they're large enough that we can treat them classically using classical methods. We don't need to go to quantum mechanics to describe how the particles interact. Okay, so the two things that I'll be interested in this talk will be, one, how can we describe, if we have a collection of such particles, how can we describe its stationary distribution? So in other words, if we let the system evolve under thermal fluctuations for a long time with no additional forcing, what's the probability of finding the system in a given state? And that stationary distribution is just the Boltzmann distribution, where U of x is the internal energy, x is the list of sort of particle coordinates, and then T is the temperature. And the internal energy, for many kinds of such particle systems, a good model for the internal energy is a sum of pair interactions between particles. So this here represents sort of a pair potential between particles I and particles J. And this pair potential can come from numerous different types of physics. It can have repulsive parts that arise because of electrostatic interactions, steric interactions, et cetera. It can also have attractive parts that make particles stick together, and I'll talk about attractive parts on the next slide. Another thing we might be interested in is dynamics. So what is the dynamic? What are the dynamical pathways that a system of particles follows? We might be interested in dynamics, for example, to understand how polymers crumple up, how crystals nucleate and grow, et cetera, how a network of actin fibers responds under forces. And a good model for the dynamics is this following stochastic differential equation. So this says that the collection of particles slides down the gradient of the potential, and then it's also jiggled around by random noise. And gamma here is a parameter that models the friction that the particles feel because they're in a fluid. They're often in a fluid. And I will point out that usually gamma depends on x, in which case these equations are a little bit more complicated, but I'm going to ignore that dependence for most of this talk. Okay, so a very important feature of the attractive interaction that will be important for this talk is that when particles like to stick, the range over which they feel each other and want to stick to each other tends to be very short compared to the particle's diameter. So here I'm showing a sketch of a pair potential that was estimated for a particular experiment. It happens to be an experiment that looked at colloids, these big particles, interacting with a depletion interaction, which are the much smaller particles here. And when you put a lot of smaller particles, these are sort of bundles of polymers, in a solution with bigger particles, it creates an entropic interaction that tends to push the big particles close together, but only when they're within roughly the size of the smaller particles. So in this particular experiment, the width of the interaction potential was only a few % of the diameters of the particles, and we're interested in describing sort of motion over the scales of particle diameters. I'm also plotting, so for comparison, a Leonard-Jones potential, which is often thought of as a short-range potential, at least in atoms. And I'm plotting it on the same scale as this. And you can see that even the Leonard-Jones potential, the 612 Leonard-Jones potential, is much sort of longer range than a typical potential governing colloid interactions. So another way colloids can stick together is by covalent bonds. These are also notoriously stiff interaction potentials. And finally, another thing that you can do to make them stick together is glue them with ligands and receptors. And so in other words, if you have a particle and it's coated with sort of sticky hairs, then those hairs, if they can stick to receptors on another surface, that will create an effective interaction potential between the particle and that other surface. And this is a mechanism used in a lot of biological systems. I'm showing an image of a white blood cell here. This is actually how white blood cells exit our bloodstream. They first take their sticky ligands, they stick to receptors on the surface of our blood vessel, and then they eventually get desorbed. But it's also a mechanism that's useful in materials science, and there's a number of experimental groups that are building systems of colloids with programmable interactions, so interactions that you can control. And the way they do that is they glue DNA strands on the surfaces of the colloids, and single-stranded DNA strands. And if the single-stranded DNA strands have different codes on different particles, then when the particles get together, the DNA strands will hybridize, and so the particles will stick. And so by sprinkling sort of DNA strands with different kinds of codes on different particles, you can in principle create particles with sort of whatever type of interaction structure you want. In practice, it's actually hard to do that with a lot of control, but in principle, that's the goal. And using this technique, experimentalists have managed to reproduce many, if not most, of the crystal structures that you find in nature, but synthesized with much larger particles, so synthesized with nanoscale or micron scale particles. Now, this image is a schematic, and it's not to scale. Here's an example of an image that this is this is an image that is to scale. This image was generated by a postdoc in my group, Sophie Marbach. And you can see, this is a DNA-coded colloid, a 400 nanometer DNA-coded colloid. You can see that the DNA strands are much shorter than the size of the particle. What you can't see is that the DNA strands are actually not very compressible. They're not very squishy. So when the particle is on the surface, the polymer brush doesn't like to compress very much. And we've estimated that the range over which you can compress it, hence the range of the interaction, is roughly 1 to 2 nanometers. So really a lot smaller than the size of the particle. So I will mention this is somewhat of a tangent, but since this is a computational science seminar, simulating a particle such as this with so many DNA strands on it is computationally infeasible. So one thing that my group is interested in is deriving sort of effective equations that average over these DNA strands and describe the dynamics of a particle moving on this sort of rough, sticky surface. But I won't talk about that here. So given that we have attractive interactions that are so narrow, well, this is a problem for computations. Because it's hard to resolve that interaction potential. So if we're interested in generating samples from the Boltzmann distribution, say we do that by a Monte Carlo method, well, it's going to be very hard. We have to propose very small moves in our Monte Carlo method, because otherwise we'll break a bond or several bonds, and then we'll have a large rejection rate. I will point out that there are sort of special schemes that have been developed to handle this, particularly in disordered systems like liquids. But these schemes are not generalizable. So we can't apply them to simulate something with a backbone, for example, or to study crystal nucleation, where we're interested in sort of the much more ordered structure of a crystal nucleus. It's also a challenge if we're simulating a dynamical equation, because then we have to take a very small time step, say delta t, in order to resolve this rapidly varying interaction potential. So in a recent project where we wanted to simulate dynamics, we had to take a time step of about 10 to the minus 3 seconds, which doesn't sound so bad, except we needed to simulate the system for orders of days, so many, many orders of magnitude longer. And furthermore, we wanted to simulate the system many times to generate statistics, and we wanted to solve design problems, so somehow solve optimization problems on top of this. So it took us like weeks and weeks and weeks, more than a month to do this. And most of this computational time is just spent jiggling the little bonds around, vibrating the bonds, and not making any interesting displacements. So it's just a huge waste of computational power to do this. So we'd like to address this challenge, and that's what one topic that my group works on. One strategy for a natural idea for addressing this challenge is to take these sort of rapidly vibrating bonds and just replace them with constraints. To say, okay, if I have two particles that are bonded, let's call that a distance constraint. And then we can take moves that are sort of orthogonal to that distance constraint. Hopefully we can take larger moves that way. And so this is a natural idea, and it's been around for a long time. I think sort of shake and rattle algorithms in molecular dynamics were the first ones to kind of promote this. And these algorithms are still widely used to this day. And there have been numerous other algorithms that have been developed in sort of explore this idea in other kinds of situations as well. One thing that none of these algorithms can do is handle constraints that can break and form over the course of a simulation. So if we have particles that are forming a bond, but then they're also breaking a bond, and then maybe later they'll form it again, they'll break it again, et cetera, we can't handle that kind of situation with any of the methods that have been developed so far. So that's the topic that my group is interested in. How can we simulate stochastic systems that have constraints that are variable, i.e. they can break and form over the course of a simulation? Okay, so I'll talk about some of the work we've done towards this goal. First, I'll talk about a Monte Carlo method to sample from the stationary distribution, this Boltzmann distribution. And then I'll talk about our initial work on simulating dynamics. And it's somewhat preliminary, but I want to talk about it because it uses some interesting mathematics, and it's just some interesting mathematics problems. And then if there's time, I'm going to talk about some of the fundamental problems with using constraints in certain situations that are sort of limiting in those situations, but that are also, I think, interesting and beautiful mathematical problems. And please stop me at any time if you have questions. Okay, so first, how can we sample from a stationary distribution of a system that has constraints, but where these constraints can break and form? So I'm actually going to pose this describe this in a situation slightly more general than particles interacting with pair potentials. And I'm going to talk about a method to sample from a stratification, which is a collection of manifolds of different dimensions, such that some manifolds form the boundaries for higher dimensional manifolds. So first, I'm going to explain what a stratification is and how it arises from systems of particles with pair interactions. Okay, so let's think about a very simple system. We're going to think about 3 disks in the plane, 1, 2, 3, and they have pair potentials between them. And here's the Boltzmann distribution, okay? And I'm going to assume that this pair potential, so they all want to stick to each other, but only when they're really close. If they're not really close, then they don't feel each other at all, and they'd move around, without any interactions. And I'm going to look at the limit. I'm going to consider pair potentials that are very, very narrow, and I'm going to let that narrowness, that width, go to 0. And then I'm going to let the depth be quite deep, so the interaction is strong, and I'm going to let that depth go to infinity. I'm going to assume that there's a cutoff here, so the interaction potential is like 0 when they're out of the interaction well. And then I'm also going to assume that the integral of the Boltzmann distribution over this narrow interaction potential approaches some constant, which is not 0 and not infinity. It's some constant, which I'll call kappa. And sort of by design, these assumptions force this Boltzmann factor for single pair potential to approach a delta function, right? I'm sort of making it approach a delta function, where the argument of the delta function is some function that measures the distance between the particles' surfaces. Okay, so here I've written it as xi minus xj squared minus their diameter squared. Okay, so when this is 0, then the particles are exactly in contact, and I have some delta function for being in contact. And then I also have a +1 because of this part of the pair potential where the particles don't see each other. Okay, so in this limit, I actually end up with a stationary distribution that has, if I multiply out all these delta functions, then I have a stationary distribution which has support on sets of a variety of different dimensions. So when none of the particles are in contact, there's some finite probability of being in this set where none of the particles are in contact. And this is a 6-dimensional set because each particle has 2 degrees of freedom. There's also some finite probability of finding disks 1 and 2 exactly in contact. And I can, this is a 5-dimensional set because I can move disk 3 in 2 dimensions, and then I can move this around and rotate it. That gives me 3 degrees of freedom. And so on. As I form more and more contacts, I lower the dimension of the set that I'm interested in. Okay? And so we actually, so each of these configuration spaces is a manifold, and our entire configuration space is a union of all of these different manifolds. So that's what a stratification is. Here's a slightly larger example that my former student Anthony Tribbiano worked out. This shows all the different contact graphs that you can get if you think about, excuse me, a polymer of 6 disks where the backbone is constrained, so it can't break, but then the disks can break and form any other contact that they want. And these are all the different contact graphs that you get. And we can think of this one as a 4-dimensional manifold, not a, I guess it would be 7-dimensional manifold, because if we mod out by translations and rotations, there's 2 translational degrees of freedom and 1 rotational degree of freedom. And so each of these contact graphs, as you wiggle it around, it fills up a 3-dimensional manifold. Similarly, each of these ones will fill up a 2-dimensional manifold, and so on, down to these ones, which we can think of as just points, so 0-dimensional manifolds. Okay, so I'd like to generalize this to be able to talk about more than just particles, because constraints arise in a variety of situations. Even for particles, we might want to talk about bond constraints or being constrained to a surface. But constraints also arise in statistics. sort of solving inference problems in statistics. In machine learning, if we're looking for weights in neural networks, sometimes it's convenient to impose constraints on those weights and then to vary those constraints, and so on. So how do we generalize this? Well, I'm going to start with a list of functions. So for particles, these might be the functions that measure the distance between pairs surfaces. And then to form one manifold, what I do is I identify some of these functions as constraints and then some other functions as inequalities if I want to. And then I can form a manifold by saying, OK, it's the set of all points in configuration space such that the constraint functions equal 0 and the inequality functions are greater than 0. And I have to make an assumption on my constraint functions in order to do anything at all with this. And that assumption is that if I look at the Jacobian of the constraint functions, then this matrix has full rank everywhere on M, everywhere on the set M. And that assumption is really critical, and it doesn't always hold. I'll show you interesting examples at the end of the talk where it doesn't hold, but we can't make progress without it. So I will make that assumption. And under this assumption, M is a manifold. It's actually a Riemannian manifold, so it has some nice geometrical structure. And we can proceed and do computations with it quite nicely. So that gives me one manifold, and then by choosing different labels, so different identifications of constraints and inequalities, I can form different manifolds, and then my stratification is the union of all of these different manifolds for each different sort of labeling of the constraints. Okay, so stratification is a geometrical object, and then on top of that, I'm going to put a probability measure, and I construct the probability measure by starting with the surface measure, mu I, of each of these manifolds. So each manifold has a sort of a natural way of measuring surface area on it. And I might want to weight those surface measures by something. It might be some Boltzmann factor or something. So then my probability measure is sort of a weighted sum of all these different surface measures. And this is the thing that I would like to generate samples from, this probability measure. Okay, so what I'll show you is a method to generate a Markov chain whose stationary distribution is this measure. Okay, are there any questions so far? Okay, so this is an example just to sort of illustrate the notation. It has absolutely no physical meaning. But let's suppose my constraint functions are y minus x squared and then 2 minus y. And if I can construct a stratification by thinking about all the possible ways to label these as constraints and inequalities. So if they're both inequalities, then I get this blue region, which is two-dimensional. And the surface measure of this region is just the regular sort of area measure. If I label one of them as an equality and the other as an inequality, I get this sort of segment of a parabola. And this is a one-dimensional manifold. And the surface measure on this is just the arc length measure. It measures like how long the piece of arc length is. And similarly, I can reverse that to get this one. If they're both equalities, then I get zero-dimensional manifolds, which are points. And the surface measure on those is just the counting measure. How many points do I have? I've generated points using our stratification sampler, which sampled a probability distribution, which is just the sum of all of the different surface area measures. And you can see it generates some points in the middle, some points exactly on the parabola, some points exactly on the line, and then these points were exactly on the corners, but I blew them up a little bit so you could see them. OK, so that's just to have sort of a picture of what a low-dimensional picture of what a stratification is. So now, how do we actually sort of go about building a method that samples from that probability distribution? We're going to do this using a regular Monte Carlo method. So we start with a point x and then label I, and then we propose a new point and label combination. So we first propose a label, i.e. a new manifold, and then once we decide which manifold we want to move to, we propose a point on that manifold. Okay? There's some density of probability of proposing labels, densities of proposing points on a manifold, which we assume we can calculate. And then we do an acceptance rejection step. And this is the usual sort of Metropolis-Hastings formula for accepting and rejecting. If we reject, you go back to the beginning and try again. The only difference here from regular Metropolis-Hastings is that these are actually densities with respect to different measures. But that ends up being OK. You can show this whole thing satisfies detailed balance. Hence, it has the correct stationary distribution. So, of course, this is kind of a high-level description of Monte Carlo methods. Yeah?
On the previous slide, what is the size of the capital Q?
What is the size of capital Q?
Yes, the number of the Qs. Okay, here it's 2, but in
Yes.
general...
Yes. So you're right. For a large collection of particles, you would not want to list out all the Qs, because you would not want to list out all the pair interactions.
Okay,
Yeah.
so by default, you are focusing on some interactions more than others. For this to scale.
Yeah. So if we have a larger collection of particles, we don't actually list out all the Qs. We have we can detect when we're close to a boundary where a new Q will form or not, and then we can decide to sort of add that in or not. We only keep track of the Qs that are active at a current time, and then we can detect whether we're sort of close to a point where another Q could form or not, and if so, then we add it to our set. Yeah, but you're right that getting this to scale to high dimensions is still something we're working on, because there's a number of numerical issues that have to be dealt with to make it work to make it work efficiently in high dimensions. Yeah. Okay, so in order to implement this Monte Carlo method, there's sort of I won't go into all the sort of details of how to do this, but there's a few things we need to be careful about. One is that there's for given point x and then its proposal y, we need to make sure that there's unique mapping from x to y and then from y to x in order to calculate the acceptance probability. And this is something that's not 100% trivial when you're jumping between manifolds of different dimensions. We need to make sure we can calculate the densities involved in the metropolis ratio, and we need to make sure that those calculations are not too expensive, otherwise this will slow us down. And we need to make sure that our overall acceptance probability is not too low, because then we waste a lot of time proposing moves, and that slows us down as well. So here's sort of an overview of what goes into this. So we have 3 types of moves. On one kind of move, we just move on the manifold, the current manifold. We don't change the manifold. And then a related move is what I call a gain move. We gain a dimension, and we do that by dropping one of the constraints in our constraint set. And then we just move on the manifold that we get by dropping that constraint. And so those 2 moves are the same at a high level. And the way they work is as follows. Once we've identified the manifold that we're moving on, so we're at some point x. You see my mouse. So I'm at some point x, and I'm moving on this sort of curved manifold. I propose a step v in the tangent space to the manifold, and I can find the tangent space using linear algebra. And then usually that will push me off the manifold because it's curved, so I need to find my way back down to the manifold. So I do a projection step, and I find a vector w such that v plus w puts me back on the manifold. And I require that w be in the normal space at x. Okay, so we can do this by solving a nonlinear system of equations. So the requirement that w be in the normal space at x, well, the normal space is spanned by the gradients of the constraints. And if there's m constraints, then I have m variables to solve for to describe w. But I also have m equations that describe my manifold. So in general, this system of equations is well posed. And in general, it has isolated solutions. So this we call the projection step. Now, there's other ways to do projections. You might wonder why we don't find the closest point on the manifold, which would be another natural way to do a projection. And that would be asking that the step be in the normal space at y. And this kind of projection has a few advantages. So we found that when we do this kind of projection, we never need to calculate second derivatives, i.e. Hessians of our constraint functions. We can calculate the proposal density for the move, and we can solve the nonlinear system equations using only first derivatives, which is a big advantage. Another advantage is that we never have to calculate Jacobian factors. So when we work out the proposal densities, we're actually sort of changing variables a few times. To go from x to y, I first propose a move v, then I project that down. So I'm sort of distorting my area measure as I go from v space, tangent space, to y space. So there's a Jacobian involved in that I would need to calculate. But we can show that this Jacobian equals the Jacobian for the reverse move. If I'm going from y, I propose a reverse v v prime, and then I project to get x, those Jacobian factors are the same for some sort of interesting geometrical reasons. So they cancel in the metropolis ratio, so I don't need to calculate them. And so that's another big advantage. This kind of projection doesn't always work because it doesn't always exist, right? Sometimes there's just no point that intersects the manifold, or our nonlinear solver doesn't always converge if we're being a little sloppy. We don't want to throw a lot of resources at solving this problem, so we just want to do it quickly. But we can actually correct for this using the rejection step. So it's actually OK if this projection doesn't work or if our solver fails. We just reject our move, and we have to also check the reverse projection for detailed balance, but it ends up being OK. But I will say this projection step is the slowest part of the algorithm, solving this nonlinear equations, as you can imagine. So those are two kinds of moves, and then the final kind of move we do is we jump to a lower dimensional manifold. And the way we do that is we add a constraint. And so once we've decided which constraint to add, then we choose a tangent vector. Again, we choose a tangent vector in our current normal space. But now we choose only a unit tangent vector. And so, and we don't know, and then we try and take a step in that direction to find our way to this lower dimensional manifold. And so I have an extra constraint describing this manifold, but I also have an extra variable, which is the distance that we have to go to get to this surface, to get to this manifold. So we also have a system of equations that, in general, has isolated solutions. Now, when we do this, we have to be careful. If we choose our tangent vector isotropically, if we choose the angle here uniformly, then we end up with a very terrible method with lots of rejections. And the reason why is that there's a pretty big chance that we'll choose a tangent vector that is reasonably sort of parallel to this surface, that doesn't point directly to it. And then we get sent really far away, potentially very far away into this region. And if we ask, well, what's the probability of doing the reverse move? Well, if I start like here, the probability of going here is minuscule, like many orders of magnitude smaller than the probability of proposing some set of angles here. So we have to do this carefully. We can't propose isotropic moves. What we end up doing is proposing mostly moves that mostly move in the normal direction to the surface, and a little bit of tangential wiggling. And then similarly, when we move off a manifold to a higher dimensional manifold, we also move mostly in the normal direction. If we do this carefully, then we can show that we have a method that gives 100% acceptance probability for flat manifolds, and that's an advantage because then when we do this for curved manifolds, we can still take fairly large steps and obtain a reasonable acceptance probability as well. OK, so that's sort of a high-level overview of our method. Let me show you how it works on some examples. So in these movies, I'm comparing two different methods. This is a simulation of a polymer with a backbone, and the polymer can fold up and form bonds. And we're simulating this using by simulating the Brownian dynamics equations, so the overdamped Langevin equations, with a time step that doesn't lead to numerical stability, but is close to the numerical stability boundary. And here, simulating the same system, but with the stratification sampler, which can propose some really aggressive moves in configuration space. And the frame rate of these two movies is proportional to the computational time. So you're sort of seeing, can I run these again? Yeah, so as you watch these movies, you're sort of getting a visual sort of impression of how the relative efficiency of these methods works. So this is sort of what standard methods will do, and this is what our stratification sampler will do. So you see it's really a lot faster. In the time that this guy forms one bond, this guy has sort of broken and formed many, many bonds, maybe hundreds of bonds. OK. So constraints don't just have to be distance constraints. We can also think about constraints that make particles bind to surfaces and come off surfaces. They can also just be geometrical constraints that have nothing to do with particles. So just for fun, I tried to calculate the surface area of a 10-dimensional ellipse. Surface areas of ellipses actually are, there's in general no analytic formula for anything higher than roughly 3 dimensions. Maybe even 3 is, I don't know if there's a formula for it. So one way to estimate the surface area of such a sort of high dimensional surface is to construct a stratification by slicing it with planes. So slice it with one plane, gives you a lower dimensional manifold, slice it with another plane, lower dimensional manifold, and so on. You keep doing this until you get to 0 dimensional manifolds, which are points. And in this case, there's 2 points. So I know the volume of that 0 dimensional set is just 2. And so if I sample this stratification, and then I count how many points are on the surface of my ellipse divided by how many points were in my 0 dimensional sets, and I multiply that by 2, then I can estimate the surface area of the ellipse. So we can sort of use this method to do geometrical calculations as well. There's actually, you could form a better stratification just by looking at the ellipsoid and its interior, because you know the volume of the interior. But in general, you don't know the volume of a high dimensional space either. OK, so that's what I wanted to say about Monte Carlo methods. Now I want to move on and say a little bit about dynamics. So actually, our stratification sampler proposes local moves. So in principle, if we took small enough moves, it would be simulating some kind of dynamical equation. But we'd like to have a little bit more control over that. So we'd like to develop sort of a tailored method to solve dynamical equations that are consistent with the Langevin equations or the overdamped Langevin equations in some limit. So let me start by thinking about a simple example. So we'll think about a particle moving on a one-dimensional line. And this particle moves just as a Brownian motion over here. But when it gets close to the origin, then there's a pair potential or potential energy that tends to push it towards the origin. And I'm going to call this a wall, just because there's a reflecting boundary condition here, so the particle can't go through it. So the particle evolves according to this equation. And again, we're going to think about a narrow, deep, sticky potential well. And to illustrate just the numerical difficulties, let me show you a movie. I'm going to show you a movie which generated 3 trajectories to this equation. One ignored this term and just simulates a Brownian motion with a reflecting boundary. So that's the black line. Another simulated this equation with a time step of roughly 10 to the minus 7. And then another simulates this equation with a time step of roughly 10 to the minus 5. And they're all oh, will that work? There we go. They're all driven by the same Brownian motion. So you see they all agree initially as they approach the wall. They're all just Brownian motion as they approach the wall. But then when they hit the wall, the reflecting Brownian motion just reflects, but so does the method that has a time step of 10 to the minus 5. It just skips right over this potential and just wanders back off into space. Whereas the one with a smaller time step sees this potential and jiggles around near the wall before it eventually leaves again. Okay, so there's sort of quite a strict time step requirement to simulate this kind of equation. We'd like to move away from that. Okay, so what we're going to do is the same kind of asymptotic procedure. We're going to think about the limit where this interaction potential essentially approaches a delta function, the same way we did before, and ask what happens to this equation as u, or as e to the u approaches a delta function. And we're actually going to look at the Fokker-Planck equation and see what happens to the Fokker-Planck equation asymptotically. And I think I left out the slide that sort of shows the steps. But what we get in the end is this. This is the limiting equation as we sort of take the sticky limit of that pair potential. And so this is the equation for the sort of A version of the probability density of the particle. And so this part should be very familiar. It's just a diffusion equation, which is the regular Fokker-Planck equation for Brownian motion. What's unusual about this equation is it has a boundary condition at 0, which looks a little funny. Second derivative is proportional to the first derivative at 0. So that's unusual. Usually what we see is either px is 0, which would be a reflecting boundary condition, or we might see p is 0, which means the process is absorbed at 0. But here we have the second derivative is proportional to the first derivative, which is a little weird. And I find this not intuitive. I find it just hard to understand just by staring at it. It turns out that this is the boundary condition for something called sticky Brownian motion, which is a stochastic process studied in probability theory. And what it is, it's a Brownian motion that's slowed down at 0, just enough that it actually spends a finite amount of time at 0. Interestingly, it never actually spends an interval of time at 0, but the sort of measure of the set of points it spends at 0 is finite. It's not 0, it's some finite number. And that's actually what we want. So we want something that spends time at 0 as well as in a higher dimensional set. So that's good. Kind of as a mathematician, I like this boundary condition because it's something that mathematicians found first before anyone pointed out that it might be useful in physics or engineering. It was discovered by Feller in the 50s. And Feller was looking for all of the possible boundary conditions for a Brownian motion, something that looks like a Brownian motion on the half-line, but then does something at 0. What can it possibly do at 0 and still be continuous? And this is the set of boundary conditions that he found in general. And he actually says in this paper, this is the second instance of a concrete problem with physical significance where physical intuition failed, but our abstract methods provided a clue, which I think is a really nice, it's a really nice thing because it doesn't often happen that way. Usually sort of something is discovered in physics and engineering and mathematics. Mathematicians will go up and clean up afterwards. I do wish he could tell us what the first instance is, but he doesn't tell us what this first instance of a concrete problem is. OK, so we would like to simulate sticky Brownian motion. And here's another sort of cute fact about it. It solves the following stochastic differential equation. There's a force exactly at 0, but otherwise there's no force. And then away from 0, it's just Brownian motion. It evolves as Brownian motion. So this is really weird, because how can we possibly simulate a process that has a force only at one point? It kind of seems like we've made the problem worse before making it, we're trying to make it better. No standard methods will be able to discretize this equation, because almost all methods to discretize SDE work by choosing a time step and then working out a spatial step, which is random. And so since it's sort of random and continuous, it's never going to hit that one point where there's a force. So how can we deal with this? So we're actually going to take a different approach. And instead of discretizing the process in space and then working at in time and working at the spatial increment, we're going to discretize it in space and then work out the corresponding time increment. OK, so we'll discretize the real line. We'll just do it like a regular grid with spacing h between the points. And we're trying to solve for the process on the black points. So we start by looking at the generator of the process, which is the adjoint of the Fokker-Planck operator. In this case, it's the same. And we'll work out this generator. The discretized generator will approximate it using what we know about the function on these grid points. OK, so this should seem familiar to anyone who's solved a PDE numerically. We're just going to discretize this PDE operator using finite difference. So if we're in the interior of these grid points, then we can just use central difference formula to get an estimate for the generator. If we're at 0, then this formula would tell us we need to know f minus 1, but we don't know f minus 1. So then we turn to the boundary condition here to we discretize the boundary condition and use that to solve for f minus 1. And so then we get a discretization of the generator at 0. So now from this discretization, we can use this to drive a Markov jump process on this set of discretization points. And so the discretization gives us an approximate generator for this Markov jump process, which looks like this. And we can, the coefficients of the f's tell us the rates of jumping. And we can simulate a trajectory of this Markov jump process using the Gillespie algorithm. And so the way that works is, well, we look at the rates, and they tell us if we're in the interior, then I can jump to if I'm at point k, I can jump to the left or right with equal probability. And then the time that it takes me to do that is given by this diagonal coefficient. And so it will be some random exponential random variable with mean h squared over 2. So we recover the usual diffusive scaling of a diffusion process where the time is the square of your the distance you've gone. If we're at 0, then we get something different. Then we can only go to the right, so we can only go to this point. And the time it takes to do that, if h is small, is going to be roughly kappa times h. So we get a different kind of scaling here. This is a ballistic scaling. It's much, much longer if h is small. And so in particular, this is long enough that it is sort of the mean time to spend in an interval of interior points. And so that means that even when h goes to 0, the time you spend at the boundary doesn't go to 0. It remains finite, something proportional to kappa. And so I like this discretization, partly because it gives insight into this sort of peculiar stochastic process called a sticky Brownian motion. It gives insight into like what's happening at the boundary that makes it sort of sticky and actually spend finite time there. But it's also useful practically because it gives us a way to simulate this process, which is otherwise challenging to simulate. So let me show you some trajectories that we simulated with this Gillespie algorithm. You see they go, if they're not at 0, they go up and down with equal probability. And the time they spend at each point is random, but on average it's pretty short. But if it's at 0, then it tends to spend a much longer time at 0 before it moves away. And here are some examples of trajectories with much finer grid spacing. And you see this looks a lot like Brownian motion, which it should, except it's sort of slowed down at the boundary. So it's really kind of sticky there. OK, so in terms of practically how useful is this as a computational tool, the Markov jump process discretization is accurate up to very high, pretty high time steps. It converges with order h squared. And so you're not making much error if you take a large time step. Whereas an Euler-Mariema discretization using an interaction potential characteristic of different experiments will work if the time step is very small, but then is sort of completely unreasonable for larger time steps. Gives you something completely different from what you're looking for. So this suggests that this is a sort of promising way to discretize interaction potentials that are very narrow, but that can break. So this is just one dimension. How do we do this in higher dimensions? So we're working on higher dimensions. We have to first derive the equations in higher dimensions. So that we've done following similar asymptotic procedures. So the equations themselves are a little sort of, there's quite a lot involved, but just intuitively what they mean is if I'm on some manifold, like let's think about this polymer of 6 disks that can crumple up and form different contact networks. If I'm in some manifold, let's say like this one, the contact network can sort of change, and the dynamics by which it does so are first of all there's diffusion, so it jiggles around randomly on its manifold, and then second there's a forcing term. Even if there's no external force on the system, there's still an effective force that arises because these constraints come from a finite width interaction potential. We don't impose them directly. This is something I don't really want to dwell on, but it's it's a finite force that's there and remains there in the limit, even in the limit. And then it changes because it absorbs probability from higher dimensional manifolds for which it forms part of the boundary. So this guy will absorb probability from here and here. And then it will jump to here. So it's sort of what you'd expect. You get a collection of Fokker-Planck equations, one on each manifold, but they're coupled at their boundaries by these flux terms. So we know what the sort of Fokker-Planck equation and hence the generator of the processes that we're looking for. What we're working on now is actually discretizing this and making this discretization work in higher dimensions. What we have done is, so this is a high dimensional system of equations. And you might wonder if it's reasonable to model colloids. And so we've checked that. We've checked that it works by studying transition rates between colloidal clusters. So on the next slide, I'll show you, we did an experiment where we had 6 disks. They weren't actually formed in a backbone. But we had 6 disks, 6 colloids, sitting on a glass cover slip. And they like to spend time in these 3 ground states. But every so often, they'll transition between these different ground states. And as they do, they have to jump into a higher dimensional state, so like a one-dimensional manifold. So we can use this system of equations to try and predict the transition rates between these ground states. So here's a movie of our experiment. This experiment was done by a graduate student in Vinny Mataharan's lab, Rebecca Perry. You can see the colloids, they're jiggling around. This is sped up. And Rebecca also colored the colloids to prove that we could track their positions, and just to make the video a little more exciting. And you see the colloids are mostly in these 3 ground state clusters, these 3 clusters with the most contacts. But every so often they break apart, and then they form another ground state cluster. And so we counted how many times they transitioned from one to the other and got this sort of table of counts. And so then we used our system of equations to work out what these counts should be theoretically. And I'll point out that this is different from a transition state calculation, because we're not just looking at sort of the energy barrier to breaking a bond. We're also accounting for sort of the space particles diffuse around in as they transition. And to make a long story short, we have to incorporate hydrodynamics to get the numbers right. But once we measure the sort of the hydrodynamic friction associated with each transition path and incorporate that into the theory, then we get numbers that look quite a lot like the numbers that we measured. So there's no fitting parameters here, just measurements. And there's statistical error and asymptotic error, which we believe accounts for the difference between these numbers. OK, so we're still working on being able to solve dynamical equations on manifolds where you can jump between different manifolds. OK, in the remaining time, I want to point out an issue with using constraints in particle-based simulations. And this comes back to the assumption that my constraint matrix, the Jacobian of my constraints, has full rank everywhere on M. OK? So this assumption is not always true. So you had a question?
So I remember that you have to solve this system.
Yes.
Wait until the end, maybe,
Sure.
because maybe we should try to keep it like 5 minutes more, and then we
Yes,
have time
yes.
to move to questions, and
Yes.
then use the mic for the questions.
Sure.
Yep, no problem. Yep. So this assumption is not always true. One thing that can happen is you can have more constraints than are necessary, so some of them are redundant. And this, of course, happens if you're looking at crystals, like FCC crystals or HCP crystals, because here, crystals with this kind of packing have on average 6 contacts per particle, when usually you just need 3 in order to, usually particles can only form up to sort of 3 contacts on average. Here's a simple 2-dimensional contact network. Well, it's just a graph. It doesn't represent contacts, which has too many edges. So the corresponding Jacobian would not have full rank. So this is actually, maybe it would be annoying to deal with, but it's not conceptually deep to deal with. You could remove the redundant contacts and still proceed. More interesting and more challenging are constraints that, you have the right number of constraints, but they happen to be linearly dependent. So one example is this graph where the edges have fixed lengths. Those are my constraints between points. And if this blue vertex happens to be collinear with the other 2 vertices, then these 2 black edges are linearly dependent constraints. If I look at their Jacobian, they end up being linearly dependent. And one way you can see that just by mechanics is that if I take this vertex and move it perpendicular to the line, then that doesn't stretch the edges to first order in the amount that I move it by. Just by geometry, you can work that out. So this would look like a 0 mode of the Jacobian matrix. So it would look like this framework is floppy. It would look like this graph is actually floppy, has 1 degree of freedom. But it's not floppy, because I can't actually move this by any small amount and still keep all these edges the same length. And here's an example in 3 dimensions. This is a packing of 9 spheres, which has the same basic features. There's a 0 mode that looks like a 0 mode infinitesimally, but is not actually a 0 mode, not a finite 0 mode. You might say, well, why don't we just ignore these? Because probably they don't happen very often. But depending on the system you're looking at, they can occur sort of ubiquitously. So if you're looking at packings of identical spheres, then one of my experimental collaborators, Vinny Manaharn, has measured that these sort of singular sphere packings occur with quite high probability. And there's a reason for that. The reason is that these zero modes give the clusters a lot of entropy, a lot of sort of wiggle room. So that stabilizes them. That gives them higher probability of being observed. So handling these kinds of singular configurations is a challenge, because everything I told you before goes out the window. We don't even know if singular constraints define a manifold. If we do know they define a manifold, how do we determine what its dimension is? And then numerically, we can't calculate tangent space, we can't efficiently project back to the manifold, and so on. So all of our numerical tools that we've developed have to be rethought through again. And since I'm running out of time, so I won't tell you our work on this, but I will tell you that we've been thinking about what might be seen as an easier question, which is just determining whether a given graph is rigid or not, i.e. whether it's a zero-dimensional manifold or not. And that itself is actually a more challenging question than you might think. It turns out to be co-NP hard, but in some special cases, you can proceed and sort of make progress using ideas from convex programming. So I'll just leave it there for now. So I've just sort of discussed a number of sort of ideas for simulating stochastic systems with constraints that can break and form. And we'd like to sort of course, build upon these methods, make them work in higher dimensions, make them work with velocities, make them work with squishy constraints, singular constraints, and then apply them to a variety of systems that we're interested in studying. Thank you for your attention.
Well, thanks a lot. Yeah, we are going to move now to questions. So I think that we are a little bit over time, but that's OK for those of you who can stay here. Let's take questions first here. And yeah, sorry for that before. So you can go first and ask.
Yeah. So we need to solve this system because we were in that slide with that weird Q of x equals 0.
Yeah.
We jumped outside of the manifold, and then we wanted to project back.
Yeah.
Maybe it's something very easy.
You say,
why
okay.
do we jump out? Why don't we try to move on the manifold, like directly, so that we don't need to do this get out and project, so that we can skip the projection?
Because that's a good question, yeah. So for the manifolds that I'm interested in, we don't have any kind of parameterization of the manifold. So actually, if you're interested in a polymer, you can parameterize it. If you're interested in like a sphere, you can move on the surface of the sphere because you can parameterize it by angles. Torus, you can parameterize the surface of torus, but in general, there's no way to come up with variables that map, from a Euclidean space to the surface of a manifold. So we just don't know how to get to another point on the manifold without solving a system of equations. We have no way of accessing a new point on the manifold.
Okay, and I guess because this is solved numerically, it approximately lies on that surface.
Yes, so we solve it. So we actually solve it using Newton's method, and which works pretty well because we don't take steps that are enormous, so we usually can find our way back. Yeah, and we solve it to some tolerance. Yeah, exactly. So we're approximately on the manifold, and we can control how approximately that is.
Okay, very good. We can check maybe the chat and take to see if there are no questions there. So then we are good. Is there any other question here? Okay, I have just one very short question. That you mentioned that the time step was critical in the sense that if it was large enough, then other methods, they blow up. I was thinking is that really truly numerical or is a physical constraint? Because you can have a numerical constraint in a delta t, but also there are some physical mechanisms that they have some time span, and I was wondering if it could be also related to that. I assume it's not because your method, even if the time step is very large, is still stable. So I'm miscapturing the physics, so I'm assuming that the actual physical time step that is relevant is still much larger than the...
Yeah, so usually these pair potentials just jiggle bonds, and usually that's not all that physically relevant. There can be some cases where by jiggling you can actually sort of transform to another configuration with the same constraints, and you wouldn't be able to access. You're right that would actually require having like squishy constraints and simulating the squishiness as well. And in some cases, like I believe if you're looking at fiber networks, if you want to sort of stretch them out, the fact that the constraints are slightly squishy is important and does give the network some of its elasticity. Yeah.
You mentioned that these time steps, or they're usually 10 to the minus 4 seconds?
Yeah.
Oh, okay. I was surprised. That looks like a very long time for
Oh,
this
well,
type
so
of,
that, yeah, so that particular, study, we were actually simulating particles with hydrodynamics. We were using my colleague Alex Donev's code to do that. And if you have lubrication forces, so it is much longer. Normally it would be like 10 to the minus 6 or so.
Yeah.
But if you have lubrication forces between the colloids, then those forces actually help to regularize your steps. So they tend to cause the system to move along the constraint manifold anyways, so that lets you take a much larger time step. But you have to calculate all these hydrodynamic forces, which is also really expensive.
Okay, thanks a lot.
Yeah.
So thank you again for coming here in person and for this very nice talk. So
Thanks for inviting me.
And our next seminar is going to be November 18th. So just stay tuned.